we looked at series circuits and we saw that current everywhere in a series circuit was the same. So in all parts of that series circuit, the current was 0.45 amps. Now we're going to look at what happens in a parallel circuit. So in a parallel circuit, there are points or branches where the current can split. And because it can split, you've got more than one path that the current can take. So if you have a look at this circuit over here, current can go, let's go from the negative terminal of the cell. From negative, it will split over here. It will go either to the top light bulb, through the light bulb, and back to the positive terminal of the cell. That's your one option, our one branch or one loop. The other way is to go from the negative terminal of the cell, not through the top light bulb, but through the bottom light bulb, and join up over there and back to the top. So in the circuit diagram, remember the long thin lines, the positive terminal, short fat one's the negative. If we were to go from negative terminal of the cell at this point, let's make this a little bit bigger. At this point, the current's going to split. Some current will go through that light bulb and some current will go down through that light bulb. At this point over here, the current's going to join up again. So all of the current flows to that part of the circuit and all of the current flows to that part of the circuit. Along here, only some of the current flows because it's split, and along here, only some of the current will flow because it's split. If these two light bulbs are equal, meaning they've got the same resistance, then half will go through the top bulb and half will go through the bottom bulb. If they're not equal, there is a formula to calculate how much current will go through each one, and we're going to look at that in a later lesson. So let's draw this circuit, let's do the circuit online on the FET simulator. So this button on the bottom right deletes everything that we've got. Let's add in the cell. Remember the left terminal on your diagram was a positive, so we have to put our battery that same way. Then we've got connecting wire on either side of the cell. Then connecting wire going down. Got a light bulb. Well, my light bulb doesn't want to join the circuit. There we go. We've got one light bulb. Click and drag in a light bulb. You can either connect your circuit in the diamond pattern that you've seen before last year. So like that is quite fine. Or if you wanted to, you could do it in the square pattern like in the diagram that you see in your notes. So I'll do it in the square pattern to show you how to do that if you wanted. Either type is fine, square or diamond, you get to decide. So we've got square pattern on the left, diamond pattern on the right. Like I said, really doesn't matter. But I'm just going to do it in the square pattern to match the diagram that's in your notes. Okay, so I've got part of my circuit. Notice how the light bulbs are not on yet, and the reason why is because they're only connected to the positive terminal of the battery of the cell. Current will go from here around there, but no current's actually flowing because it's not a complete circuit. Only if you've got a complete circuit will current actually move. Please don't think that an electron will go from the bulb towards the positive cell and go, oh, I can't get any further than this point here. Only when you've got a closed circuit will this happen. There we go, we've got a closed circuit. Notice how the light bulbs are now on. We've got a 9-volt cell, a 10-ohm light bulb, and another 10-ohm light bulb. Now, I want you to notice, it might be a little bit laggy on my screen, but when you do this yourself, you should notice that along the series parts of this circuit, so from here, this branch and that part, and on this side, over here, up and back to the cell, the current's moving quite quickly. Whereas in the parallel branches, you'll notice that once it's split, some current goes up and some current goes down, and because of that, the current moves more slowly along the parallel branches. So less current goes to the parallel branches, whereas all of the current will go through these series parts that I'm showing you on the screen now. So all the current goes along there, and all the current goes along here. Along these parallel parts, the current splits, and that's why it's moving more slowly. So you'll see that when you draw your own circuit. Okay, let's look at what the total current is. So I'm going to put an ammeter in the series part of the circuit. It doesn't have it on your circuit diagram in your notes, but that's okay. So along that part of the circuit, we've got 1.80 amps. Let's put one on this side too, just to show you that it will also be 1.80 because all of the current is flowing through that part of the circuit, remember? Okay, so 1.80 on the left-hand side, 1.80 on the right-hand side. Now, if we've got 1.80 amps moving through the series parts of the circuit, in the parallel parts of the circuit, you should agree that it's going to be less than 1.8 amps because it's split. So let's connect an ammeter to both of those portions. 0.9 amps. Now I told you if these bulbs are equal, then the current will split equally. So if you've got 1.8 amps going through the series part of the circuit and 0.9 going through the parallel part, you should agree that the two together must add up to be, these two parallel parts of the circuit should add up to give you the total. So if that's 0.9, this should also be 0.9. Let's have a look and see what it is. If I connect an ammeter in there, it's also 0.9 amps. On this side, 0.9 amps, 0.9 amps, 0.9 amps. So along the parallel branches of the circuit, you've got 0.9 amps flowing in either branch, and it joins up over here. You can see how the electrons join together over there, and then it starts moving faster, and you've got 1.8 amps. So from this, you should be able to say that current splits in a parallel circuit. So here we go, parallel circuit. Current splits into different paths. The reading on an ammeter on the series part of the circuit, so if this ammeter here is equal to those two added together, ammeter A1 plus ammeter added A2, if you add up A1 plus A2, it'll give you the reading on that ammeter there. So let's show you again on this online circuit. 0.9 for this branch, 0.9 for that branch will give us 1.8. If I wanted, I could put in another ammeter on this branch too. Notice how I've broken the circuit. You can clearly see that current can't go from here to the bulb, yet the other bulb is on. So if one bulb breaks, meaning if this bulb breaks or is disconnected, the other bulb keeps on working in a parallel circuit. If I did that in a series circuit, that wouldn't happen. Okay, so 0.9, 0.9, that combines together to give you 1.8. So we can say that the main current is shared between the two resistors, resistor X and resistor Y. Notice how in your notes, resistor X is 3 ohms and resistor Y is 1 ohm. When that happens, when you've got different resistors connected in parallel, more current will go through the resistor with least resistance. That means that the current on ammeter A2 will be more than ammeter A1 because this resistor's only got a resistance of 1 ohm, whereas resistor X has got a resistance of 3 ohms. So it's harder for the current to get through that resistor because it's got a higher resistance. So you can make a little note on this side to say that current splits in a parallel circuit. Current splits in the branches of a parallel circuit. Current splits in the branches of a parallel circuit. Okay. So now we've looked at what happens with current, let's have a look at what happens with potential difference. So in a series circuit, I will draw a series circuit again. What this is saying is that the voltmeter reading for across both resistors, this one here, which is connected from X across X and Y, will equal the voltmeter reading for just resistor X and just resistor Y. Let's have a look at how that works. I need to draw a series circuit. Okay, so we're going to draw the series circuit on the top of page 4. We've got two cells connected in series this time. The left-hand side is the positive side. So we're just going to add two cells, connect them end to end. Then some conducting wire on either side. And we're going to go down. Some more conducting wire. Then we've got a resistor. So you can add in a resistor. Select the resistance of it to be 3 ohms because that's what it says in your notes. So use the slider to set the resistance. Then another piece of conducting wire. And another resistor. The resistance of resistor Y is only 1 ohm. So set the resistance of resistor Y to be 1 ohm. You can put a tick in this box to say that you want to see the values. Alright, now you can see the current moving through your circuit. Notice how just before this resistor, the current is moving at the same speed as after the resistor and before the 3 ohm resistor, and the current speed is also the same after the 3 ohm resistor. So the current throughout your series circuit is the same. Don't think that before the resistor with more resistance, don't think that before this 3 ohm resistor the current is greater. It's not. It's the same throughout your circuit. Let's have a look at the potential difference of our battery. So if I connected it across just one cell, so I'm going to connect the negative lead to the negative terminal, we get 9 volts, and that matches with the label that's on the diagram. And across the other one is also 9 volts. So if I connect the voltmeter across both of them, I get a potential difference of 18 volts. So my potential difference is 18 volts. If I moved the leads to these positions, notice how it's still 18 volts, and because the reason for that is that we haven't crossed over any component. We're still in the same piece of conducting wire. So whether I move this to there, or to there, or to there, or even over here, the potential difference is still 18 volts. I can move this one to there and it'll still be 18, and over there will be 18. So now I've actually connected the voltmeter across both resistors together. Remember, if I put it back by the battery, we haven't crossed over any component, and going from there along, down, and I haven't crossed over a battery or a light bulb. In going from the positive terminal of the cell up to this resistor, I haven't crossed over any batteries or cells or light bulbs. So that's why the potential difference is the same. Now let's see what the potential difference is for just this resistor. It's 4.5 volts. Notice that that's not half of the 18 that we had when I connected the voltmeter across both resistors. So 4.5 volts is for this resistor. So on your diagram, you can even put little labels in. You can say that this is 18 volts. If I were to add a voltmeter across here, it would be 18 volts. Let me do that for you guys. So if I added a voltmeter over there, it would be 18 volts. So you can add that to your diagram. And this resistor for V2 is going to be 4.5 volts. So that's 4.5 volts for V2. Now I want you to have a look and think, if the total is 18, this will also be 18. What will the value on V1 be? Well, obviously it's going to be 18 minus 4.5. 18 minus 4.5 is going to give us 13.5 volts. And if I connect the voltmeter across that resistor, it is indeed 13.5 volts. So on your diagram, you can add that the reading for voltmeter 1 is 13.5. 13.5 volts. And notice how 13.5 plus 4.5 gives you 18. So we can say that the reading on voltmeter 1 is, if you add the reading on voltmeter 1 to the reading on voltmeter 2, you're going to get the reading on voltmeter V, which is connected across both resistors in the series circuit. So potential difference is shared by resistors in a series circuit. If you wanted, let's do a little extension. Let's add a light bulb to our circuit. Okay, so I've got a light bulb as well. Notice how the potential difference across the 3 ohm resistor is now 3.86. And over here now it's 1.29. And if I add 1.29 plus 3.86, I will get 5.14. Okay, and now let's see what happens if I also add the reading on the voltmeter when I connect the voltmeter across this light bulb. Positive terminal of the voltmeter must be connected on the side of the light bulb that's connected to the positive terminal of the battery. So there's the positive terminal of the battery. It's connected to the positive side of the light bulb. If I do it the other way around, you simply get a negative reading on your voltmeter. Notice how now I'm getting minus 12.86 volts. So if I take the 1.29 plus the 3.86 plus 12.86, let's swap this around so that it's correct. If I add up all of those together, I get 18, which is the same as if I connect this voltmeter over there. So the potential difference across this light bulb plus the potential difference across that resistor plus the potential difference across that resistor adds up to the total potential difference of the two cells added together. 18 volts, that is a part of 18, that's a part of 18, and that's a part of 18. If I add up the 1.29, the 3.86, and the value that I got for the last one, 12. What did we have? 12.86, you get 18 volts. So in your notes, I want you to make a note that the potential difference is shared by resistors in a series circuit. Potential difference is shared in a series circuit. For the second part of this video, we're going to look at a parallel circuit. So I'm using the same one that we had from before. We've got a 9-volt cell. Let's add in a second one because in your diagram in your notes, you've got 2 cells connected in series. Okay, so there we go. We've got 2 cells now connected in series. Notice it's an open circuit, no paralleling. All right, we've now got our light bulbs. Notice how the bulbs are brighter here than they were when you've only got one bulb connected in series. The reason why is because if you've got 2 resistors connected in parallel, the resistance will actually decrease because there's more paths for the current to take. I'll elaborate more on that in another video, but here let's have a look at the potential difference across this bulb. It's 18, minus 18 because I've connected the terminals the wrong way around. Alright, so positive 18 is the value across the bottom bulb, and across the top bulb is 18. If I connect the voltmeter across the battery, battery of 2 cells, it's also 18. Now I want you to see, if I take this lead and I move it along this part of the circuit down, I'm not crossing over any bulbs or resistors. The ammeters have got negligible resistance. I can get from the positive terminal of the battery to the positive terminal of a light bulb. Let's go back. Okay, so I managed to get from the positive terminal of the bulb back to the positive terminal of the battery without crossing any component. I can also do that and get to the positive terminal of the other bulb. Notice how the reading on the voltmeter still hasn't changed. Let's go from the negative terminal of the battery to the negative terminal of either light bulb. 18 volts, I can get from the negative terminal of the top bulb to the negative terminal of the bottom bulb without crossing over any component. So we can say that the potential difference is the same across each resistor in a parallel circuit. The potential difference is the same across each resistor in a parallel circuit. I'm not sure where that has gone, but it's on the top of your notes. So we can say that the reading on voltmeter 1 is equal to the reading on voltmeter 2. In the next lesson, we're going to have a look at what happens when one bulb goes out in a parallel and a series circuit. That will be video 3 of lesson 1.